Welcome back to our heat transfer class, where we are delving deeper into the complex phenomenon of convection heat transfer. This video was made with the support of InnoEnergy. In the first lesson, we have seen the physical phenomenon of convective heat transfer, the different types of convection, the velocity boundary layer and the thermal boundary layer, as well as what the convection coefficient is. How is it calculated? What are the typical values? And what is the range of applicability of the formulas to calculate it? In this lesson, we delve into convection in ducts. We want to determine how to calculate the convection coefficient for convection without phase change in turbulent regime. In previous lessons, we saw, for forced convection, that we can use formulas to calculate the Nusselt number based on the Reynolds and Prandtl numbers. But is this enough? Let's start by looking at what happens at the entrance of the duct. In the circulation inside ducts, a very important aspect is the entry effect. When the fluid enters the duct, it takes a certain distance for the velocity profiles to stabilize. At the entrance, the boundary layer is very thin. It grows until it covers the entire duct cross-section and reaches a stabilized profile. The same thing happens with temperature. It requires a certain distance from the entrance to stabilize the temperature distribution. In this figure, both profiles, velocity and temperature, start their development simultaneously. In this figure, there is an isothermal zone where the velocity profile stabilizes and, subsequently, the heat transfer and the stabilization of the temperature distribution begins. This entry zone is of special relevance for the calculation of the average convection coefficient, since in the initial zone the coefficient will be greater than in the stabilized zone. That is why we will incorporate a correction factor for the input effect in the Nusselt number calculation formula. Average values of velocity and temperature. For each section of tube, the velocity and temperature vary with the distance from the axis of the tube. However, we are interested in having an average value for each section. We can integrate the mass balance into a differential control volume to get the average velocity, and integrate the enthalpy balance into the differential control volume to obtain the bulk temperature. In this way, we will have a function in which the temperature only depends on x. Friction coefficient and pressure drop. The mass flow rate, m, refers to kilos per second and is equal to the velocity times the density times the cross-section of the duct. The product of velocity times density is the mass velocity, g. Because of conservation of mass, the product of velocity times density is constant throughout the tube, even though the fluid changes temperature. To calculate the Reynolds number, we will use the mass velocity, g, instead of the velocity, with the properties calculated at the average temperature between the initial and the final temperature. For the coefficient of friction in smooth tubes and turbulent regime, we will use the Petoukov's formula. For rough ducts, other formulas should be used depending on the roughness. The range of applicability of the Petoukov formula includes the turbulent regime and Prandtl number values between 0.5 and 2000. Finally, we have the pressure drop along the duct. In this formula appears a factor phi that takes into account the variation of the properties of the fluid with temperature in the area close to the wall of the duct. We will define the factor phi in the next section when talking about the Nusselt number. The Nusselt number. To calculate the Nusselt number, and later, the convection coefficient, we will always use the Nielinski formula in a turbulent regime inside ducts. The Nusselt number depends on the friction coefficient since heat transfer is strongly influenced by flow characteristics. of the Reynolds number, which includes velocity, density, and viscosity, and the Prandtl number that includes viscosity, specific heat, and thermal conductivity. We thus see, as said in the lesson of Introduction to Convection, that the convection coefficient basically depends on the fluid velocity and its properties. Two correction factors are incorporated into the Nyolinsky formula. The entry effect correction factor. Effect explained when talking about the stabilization of velocity and temperature profiles. For short tubes, the average convection coefficient will be higher than for long tubes. The way to discriminate the length of the duct is taking its relationship with the diameter. The second correction factor is the phi factor, which takes into account the variation in the properties of the fluid as it flows over the wall of the duct. This factor takes into account the distortion of the velocity profile due to the variation of density and viscosity in the contact zone due to wall temperature. For gases, as the viscosity varies little and the density varies more, the quotient between the average temperature of the fluid and the temperature of the wall, both in Kelvin, derived from applying the ideal gas equation of state, is taken as a factor. For liquids, the property that varies the most is viscosity, with the factor phi being the ratio between the viscosity calculated at the mean temperature and the viscosity calculated at the wall temperature. Non-circular ducts. When the duct is not circular, can we still use the Nyolinsky formula? Yes, but using the hydraulic diameter instead of the tube diameter. Both for the calculation of the Reynolds number and for the calculation of the convection coefficient from the Nusselt number. When the thermal perimeter and the hydraulic perimeter are not equal, we apply a correction according to the Hausen and Doble formula. You can apply everything learned here when solving convection problems.